So in this video, we're going to very briefly talk about background functions. Now, as we said previously, we can think of our diffraction pattern as a series of peaks sitting on this background function. And therefore, the quality of our fit and getting a good quality fit is going to require us to have a good fit to the background with some sort of background function. Now, typically, the way that we do this is by using some sort of just arbitrary function to fit what we see in the background. And very commonly what we use is something called a shifted Chebyshev polynomial. Now, if you've come across polynomials before, you could probably think of them just in terms of an expansion, in terms of terms like x, x squared, x cubed, and things like that. In a shifted Chebyshev, we're doing exactly the same thing, but instead of using x squared, we use a different series of expanding terms. And in the notes, there's an example of this. But you could use any number of functions in order to fit that background theoretically. And all we've got here is just a simple mathematical expression that shows our background function is equal to the sum of a number of terms, each of which has a parameter associated with it. And so what we could do is we could change this number of terms in the polynomial that we're expanding, and we could change each of those parameters associated with it. So when we do our refinement, what we'll want to think about is how many terms we're including in that. And this will be important for capturing the subtle features potentially that we might see within the background. It's worth also just mentioning that the background can contain useful information within itself, and it can contain, for example, diffuse scattering information. If we think about a crystal at 0 degrees Kelvin, measured with a neutron source, every atom is sitting on its idealized site, and what we'd expect to see in the diffraction pattern are a series of very sharp peaks. As we increase the temperature and those atoms begin to oscillate and move off their idealized sites, we see a decay in the Bragg peaks, which is the Debye-Waller factor decay that we would expect to see. But as we go further and further, this decay increases until we remove our Bragg peaks entirely. And all we end up with is this diffuse signal, this sort of wibbly-wobbly background function that we see here. But actually encoded within that is information about the local structure within the system. And actually we can think of any diffraction pattern as incorporating both the Bragg and the diffuse. And while the Bragg gives us information about that crystallographic structure, the diffuse information gives us information on the local structure, and is, for example, what we would see in a glass where we would see just the diffuse and no Bragg. But we can see that even in a diffraction pattern like this, we can get we can observe some sort of diffuse signal in here. Now, normally, typically what we do with most diffraction patterns is we just fit that with one of our background functions that we were talking about here. So something like a shifted Chebyshev polynomial. However, sometimes that might be what we're interested in, and that opens up a whole new separate area of study that is far beyond the scope of this course. As far as we're concerned for this course, what we're interested in is just fitting that background with some sort of polynomial function, and thinking about how many terms we're going to need in that polynomial in order to capture what we're seeing in the background, and then refining those parameters associated with each of those terms in order to create a good fit to the background, so we can then focus on the Bragg peaks that we have on top and then get a good fit of those from our crystal structure that we've put in, and so create a good fit to the data and get information about the crystallographic material that we're interested in studying.